In today's video, we are going over SN2 versus E2 reactions. And let's just go over the generic schematic of this. So if you have some alkyl group here, we have a leaving group. We've talked about these leaving groups being able to hold that negative charge, right? And so these are conjugate bases of strong acids. And if we think about these alkyl groups with the leaving group, they can undergo two different mechanisms when we have a really good Lewis base, is what I'm going to call it here. So plus a good or moderately good Lewis base. And when we think of Lewis bases, remember that these are the things that can donate electrons, okay? They give electrons. So when we think of something that gives electrons, we think about something that has electrons, like a nucleophile or a base, a Bronsted base. All right, so let's go through these. So on the top, we're going to write SN2, okay, and this bottom one will be E2. Let's just draw our products that we expect from this. For SN2, we're going to be using a nucleophile. And for the E2, this is when we're going to be using our nucleophile, but it's going to be a base, all right? So nucleophiles and bases, they tend to have very similar properties. Let's draw out our products. Again, this is just kind of a schematic so we can get on the same page. So SN2, we see that the leaving group leaves, and then we have a nucleophile attached at that same carbon. For an E2, we know that we're doing an elimination reaction. So we are going to be getting an alkene. All right, so remember that this is substitution and the E2 is elimination, making alkenes. Now with this in mind, let's talk about how do you know if an SN2 or an E2 is favored. So which one? We're going to talk about that in this video. Let's walk through two different experiments here. We're going to take 2-bromopropane, all right? Now, this isn't chiral, so I'm drawing everything just in lines, but you could also draw a wedge or a dash on, well, any of these substituents, either the methyls or the bromine. So we're going to take, on this first example, we're going to take sodium methylthiolate, sodium methylthiolate. Now, when we look at this, remember that sodium, potassium, or lithium, we put our positive charge here and our negative charge on the sulfur. It's just a nice little thing to remind you that this is an ionic bond. The sulfur here is negatively charged, and we know that it can act as a good nucleophile. And I'm going to write that it's also a moderate base. Not the best base. We'll talk again using our pKa's to talk about this. The major product from this reaction is going to be an SN2 reaction. Where we essentially replace that bromine with our thiolate. Let's walk through the arrows here to practice. So this is SN2. We're going to take our nucleophile. It's acting as a nucleophile in this case. We're going to attack our carbon with the leaving group. Remember, this is our alpha carbon. We're going to make the leaving group leave. Remember that this is concerted. Happens all at the same time. Now, we can also do an E2 reaction on the same starting material. Notice I have the same starting material here. So you could also do an E2 reaction. E2 and SN2 do compete. However, when you have a really good nucleophile that isn't that great of a base, this is our major product. The SN2 is our major. The way to make an E2 reaction the major product is to use a stronger base. And since we're not adding that base to the group, we don't care really what it looks like. We're just trying to get the alkene. So if you're trying to get the alkene product, then you're going to want to use a stronger base. All right, let's draw in a stronger base here. We're going to use sodium ethoxide. The only difference here, let's use sodium ethoxide. Sorry if you drew that in pen. The only difference here is that we have an oxygen instead of a sulfur, okay? Now, this sodium ethoxide is a good nucleophile, but it's also a very good base. So actually what happens is we're going to get a little more of that E2 elimination product. All right, so let's walk through the mechanism. And we know that we have to use an anticoplanar proton here on this compound. So I'm just going to draw in a wedge on our bromine. Remember, this is not a chiral center, so it doesn't matter. We can reorient this molecule with the bromine forward or back. There's no chiral center here. And then what we're going to do is I'm going to draw in our hydrogens here on our beta carbon. So we have alpha. And this is our beta carbon. So we're going to deprotonate at that beta position, and it's going to be opposite this anticoplanar relationship with the bromine. Now, we're going to talk more about this in the next video. So on this compound, we didn't have to worry about it too much, but it is something to keep in mind. I'm going to take the proton here with the oxygen of the OMe, or the methoxide anion. Then the second arrow here is going to be making a new double bond. The carbon that's at the alpha just gained a new bond, right? It already had 4 bonds there. We know that we have this proton that's hiding out. We've got this hydrogen here. Already has 4 bonds. It has to now lose something. Notice here the SN2 has 2 arrows. The E2 has 3. That's something that you can kind of, a nice little note-keeping thing to remember. But we're making an alkene, all right? So let's draw what we have from here. So we have 3 carbons in our starting material, so we're going to get 3 carbons here. That didn't change. The only thing is we lost a hydrogen and a bromide anion. So we have our alkene as the major product. Now, we're talking about SN2 versus E2. So I should note that you do still get some elimination for these, okay? And in this reaction, you definitely get some SN2, products from an SN2 reaction, all right? But these are minor. Let's draw them in a different color. These are minor. Now, why is this? Well, we can go back to our knowledge about pKa's. So we talked about sodium methylthiolate being a moderate base, and then sodium ethoxide being a very good base. Let's look at these two. We're going to talk about the difference in the pKa of their conjugate acid. So if I look at sodium methylthiolate, and I think about its conjugate acid here, I'm going to put a proton now on the sulfur. So we're really just kind of focusing on this S minus, okay? So if we were to add a proton, you'll end up getting a thiol. And if we can do the same for our methoxide, right? We're going to add a proton, we end up getting methanol. Now, don't drink methanol. You will go blind and then die. Yeah. So, toxic. Don't do that. You need 1 more carbon, and then your body can metabolize it, albeit slowly. And it makes acetaldehyde, which gives you a hangover. But don't ever drink this. Don't do that. Bad. Okay, so pKa of these. All right. pKa of a thiol, this is around 10. pKa of an alcohol here is around 15. Now, this isn't just 5 points difference. This is 10 to the 5 more times more acidic. Now, remember when we've talked about acid versus base chemistry, when we have a stronger acid, the base is going to be a weaker base, okay? Now, when we think about this in terms of SN2 versus E2, remember that for E2, we are picking up a proton. So our side product here, it's typically just a solvent, is going to be methanol. It's really more like a solvent. Now, when we deprotonate it, we're actually making a pretty low energy, weakly acidic molecule. This is why this methoxide here is a stronger base, okay? So just keep an eye out on those conjugate pKa values. So this is a stronger base. This is due to the pKa difference. It's 10 to the 5 times stronger. All right. With this in mind, let's go ahead and go through several examples, and we're going to force the E2 reaction to happen. Now, I just talked about how you have these, both SN2 and E2 happening, but we can really favor the E2 based on using a stronger base. Now, in this case, we were looking at a secondary alkyl halide. On this next slide, we're going to talk about different carbons with the leaving group, primary, secondary, and we're going to look to see which one is favored, SN2 or E2, and we're going to use this strong base. Using a strong base, all right, so let's compare different alkyl bromides. We're going to look at different alkyl bromides, and we're going to use the same strong base that we talked about on the previous slide. We're going to use a methoxide base. Ethoxide is also very similar in its basicity. Now, if I have this alkyl bromide, I have one bromoethane. This is a primary alpha carbon, okay? We can draw both products and see which one is favored. So this will be our E2 product, and then let's draw our SN2 product over here. Now, when you run a reaction, remember these reactions in organic chemistry, they're not perfect. You almost always get side reactions and side products that you don't want. So what we're trying to do is we're trying to force one of them to be favored. And by doing so, we're also looking to see a trend. The major product for this reaction of a primary carbon with the leaving group here is going to be the SN2 reaction. In fact, it's so much major that the ratio between the two products is 1 to 99, okay? All right, let's go through another example. What happens if we add one more carbon here? Here's our beta carbon, so we've got our alpha and beta. We didn't have anything else on the beta carbon. Alpha, beta. Now we have another carbon hanging out there. Does this affect the reactivity? Well, let's find out. We're going to imagine we're going to be running this reaction. Okay, use your imagination. You can also see these reactions using solvent. The solvent here typically matches OMe, and then methanol as just a solvent. Now, the key here is that this beta carbon on this next example has another methyl group, okay? So let's draw our two products. So from the E2 reaction, we're going to have 3 carbons just like in our starting material. We're going to have our double bond. This is the one we saw in the previous slide. We're also going to draw the corresponding SN2 product. Now, when we add this additional carbon, this substituent here, check out what changed. The E2 reaction on the top example, there's no substituents here, okay, on our alkene. This is just ethylene. Here we have a monosubstituted product. I'm going to write that in purple, actually. Let's give it a different color. Okay, we have a monosubstituted alkene. This is going to increase the stability of this product. So, not so much that we end up getting a major though. So the ratio here is about 10% of the elimination. We'll add our little percent signs here. And this is around 90% of our substitution product. So SN2 is still favored. Okay, it's still the major here. What if we were to add yet another one of these substituents on our beta carbon? Let's go through that example. Let's draw our elimination product. Okay, so let's just label, just make sure we're on the same page. Here's our alpha, here's our beta. Okay, we need to lose a proton on that beta carbon, so we're going to make a double bond there. So I have 2 methyls, and then here is my alkene. That's from E2, and then our SN2 would look like this, right? We're replacing that leaving group with our nucleophile. Again, this sodium methoxide can act as a nucleophile or a base, but we're just comparing here the relative ratios. What's the major difference with the product here? Before we had a monosubstituted, and now you can see we have a disubstituted. Alkene. Well, this changes our product ratio even more. We actually get 62% of our E2 product and 38% of our SN2 product. Now, it's at this point in time you're probably asking, well, can we make it go further? And we can. So right now we're using a pretty small base, this sodium methoxide. So we're actually going to do the same reaction we have here on the bottom. So let me go ahead and copy that. You might need to pause the video to copy it on your next slide. Okay. And we're going to now use a base that's going to give us what we want. Sodium methoxide is actually a pretty small base. So in order to do this, we're going to talk about a bulky base. Let's see if I can write correctly. There we go. Bulky bases are great because they are bad nucleophiles, and we'll talk about that. Generally speaking. Okay, so on the top reaction, this is the one from the previous slide. So we're going to redraw this alkyl bromide that has 2 substituents here on the beta carbon. We're now going to use a bulky base, tert butoxide. Now on your paper it doesn't look that big, but don't forget these are CH3 groups. This thing's huge. Let's label this as our bulky base. Now, what happens here is that this isn't really that great of a nucleophile because it's so large. So what happens is we get a different distribution in our E2 versus SN2 product. Let's draw out our 2 products that could form. And here's what happens. We end up getting 92% of our disubstituted alkene and only 8% of our SN2 product. So when we think about this mechanistically wise, you want to think about this tert butoxide. It is so big. For it to come and approach, this is very difficult for it to do. So that's why the SN2 isn't favored with this bulky base. We call this having steric clash or steric interactions that makes this undesirable. As a small aside, you can actually use this base for SN2, but it's very particular. You can make this work if you have a really unhindered alpha carbon. So if we have a methyl here, and we use terbutoxide, we can end up getting SN2. Now, right now, you're probably like, oh my gosh, there's so many little caveats, but I want to show you a quick way to see that you really can only get SN2, all right? So let's back up here and think about this. So we've got an alpha carbon with a leaving group, a really bulky base. Your brain might start to think, oh, maybe I'm going to do an E2. Nope. And why is that? Well, when we look at our starting alkyl halide, check it out, we don't have a beta carbon. In fact, there's no way we can make an alkene. You need 2 carbons. So this is why only SN2 is observed for this reaction. So many times in organic chemistry, you're going to see that things aren't always 100%, and there's going to be complicated mixtures of reactions. So in this video, we talked about SN2 versus E2 reactions, and as you can see, these don't always give you clean 100% of a product. One thing to remember is that a stronger base favors E2 reactions, and using a bulky base can promote E2 over SN2. And that's because bulky bases are bad nucleophiles. All right, let's talk about one more thing about this bulky base. So I showed you a reaction where SN2 could be favored, but I want to talk a little bit about the regioselectivity of this reaction with the bulky base. Let's draw in this secondary alkyl bromide. We're going to compare the regioselectivity if we use sodium methoxide and methanol as our solvent versus the same starting material using that bulky base, that's sodium terbutoxide. Remember that sodium gets a positive charge and our oxygen here gets that negative charge. Now, if we think about this E2 reaction, I want to look specifically at the E2 reaction and what we're expecting to get as products. Now, as you can see, there's 2 different beta carbons. So we're going to get 2 different alkenes here. Now, for the beta carbon in the green, we would expect to see this terminal alkene. All right. For the beta carbon in the red, we would see 2 different products here. We could get a cis or a Z alkene, or we could also get this to be a trans alkene. So there's 3 different products here. Let's go ahead and do the same for this bottom reaction here with the sodium terbutoxide. I'm just going to cheat. I'm just going to copy this. So draw in the same 3 products because the same 3 can form. Now let's talk about what is major and which one is favored, all the good things. All right, so when we're looking at sodium methoxide, we know that this is a small base. Small but mighty. Small, good base. This is a huge good base. Huge, very large, all right? This is going to change which of these beta carbons that this is going to deprotonate. Let's review that one rule we learned. Do you remember Zaitsev's rule? The most substituted alkene is favored. Now, this is just a rule. It doesn't even talk about the specifics as to why it's favored. But on the top reaction here, this small good base with sodium methoxide, Zaitsev's rule works, and it is in line with this. Put a little green check mark there. Cool. So with this reaction, we actually do see that the major product is the most substituted. It's a major elimination product. And we see that this least substituted is the minor product. Now, what about if we use a really big base? This thing is huge. Remember that our protons here on these two different beta carbons, okay, have different steric profiles. And when we look at them, we see that the one on the bottom here, the one drawn in red, is right beside this ethyl group. And this ethyl group actually makes it less likely for this huge base to come and deprotonate it. So Zaitsev's rule isn't followed in this bottom reaction. We actually get our major product being the less substituted alkene, and then our minor product is the more substituted. The major forms with a bulky base. So the less substituted forms, the less substituted alkene forms, because this is a really bulky base. So this is just something to highlight that typically we follow Zaitsev's rule. So Zaitsev's rule is followed. Unless our base is really bulky, like terbutoxide. And so in this case, the base picks the proton that is easiest to access. So in this case, the major is coming from the protons that are on this beta carbon here. Let's just review what we just went over. Now, SN2 and E2, they both are second order in their reaction rate. Remember, these are concerted. So both the starting alkyl group with the leaving group and your base or nucleophile are present in the rate determining step and in that transition state. Now, they both need to have leaving groups. So far, E2 and SN2 are the same. The only main difference here is that the strong nucleophile works for SN2, but we need a strong base for E2, okay? This is one of the main differences between these two, okay? For E2, we must have a CH bond on that beta carbon. And we need to have it anti-coplanar. This arrangement of atoms enables this reaction to occur. SN2, we want low steric hindrance. Think about if we have an alkyl halide here on a primary, this is really good for SN2, okay? But be careful, E2 can also work because all of these are met. That's when we use something like a bulky base to favor E2. I'm going to write can favor. We still have to have that beta carbon with the CH, can favor E2. All right, so that's it for this video, and I will see you in the next video where we're going to talk about anti-coplanar and its use in E2, and I'm going to show you when you really need to be concerned about that. So here's a video of you, Rhodey's playing you, and this over there is the SN2, E2, and soon enough we'll be going SN1, E1 reactions. It's going to take a lot of work, and you have to be patient. If it's feeling like this is becoming more difficult in this class, you're exactly where you need to be. Next week, we're going to be really diving into more practice problems to show the difference between everything. And soon enough, you are going to capture, just like Rhodey did. You're going to capture all this stuff. I have faith in all of you. I know that you will do well. All right, that's it for this video. Good job, Rhodey. Good job.